My name is Prykhodchenko, and frankly, I feel a little weird today because last time I entered this facility, I became married suddenly. So I know what to expect today. So I work as a software engineer at the technical platform department at Allegro, and today I would like to tell you how we manage to distribute workload in our platform in an intelligent manner. So in order to put you in the context, I would like to briefly describe the foundation of the issue that we were trying to solve. And it's pretty easy to speak about that in Poland, because in Poland you say Allegro and everybody knows what that is. Here, of course, nobody heard about it. And Allegro is, well, you could have heard about it on the last talk. My colleague did. So Allegro works in Poland, and it's a #1 marketplace platform there. And we do have the number of accounts, active user accounts, that is more than the half of the population of the entire country. And we do have around 220 million of unique monthly visits from those users. So basically, when something is sold or purchased on the internet in Poland, there's a bigger chance that's done on our platform than anywhere else on the internet, on the Polish internet, of course. So in order to power that, we have two big data centers with thousands of assets. I was told to refrain from telling you exact numbers, unfortunately, but those are thousands of assets in those data centers. And those data centers have around 30 gigabits per second on normal day on the load balancer endpoints, and on some special events like Christmas or Black Friday or New Year Eve, this number doubles easily. We run that platform using more than 600 microservices. I think somebody created a new microservice while I was preparing this talk, so it's maybe 601. So we've been evolving that for the last 18 years. So of course, we do have a very heterogeneous environment there. And of course, we do have a lot of monolithic leftovers from the past. And when we design those services and we think about how they are going to look deployed in our production, we usually think about sort of scheme like this one. There usually is a virtual IP that covers 1, 2, or more load balancers that have some failover strategy. And those load balancers point to a specified pool of instances that actually do the job. And according to the kind of the service, we usually select we usually select an appropriate load distribution tactics like round robin or least count. Usually it's round robin, and I believe that's one of the most popular load distribution tactics in production environments. So then we try to deploy that to real infrastructure. And unfortunately, this is where the reality starts to strike, and the entire idea of this sort of deployment starts to show the first issues. And the problem is that in the past, when we used to deploy services to bare metal hardware, it was pretty easy to estimate what capacity that hardware has, and it was really easy to set the appropriate number of instances on every host and to set up the load balancer then. The reality has changed, so now every service lives in their own isolated environment. Those could be containers, those could be virtual machines, or in some cases, like we have sometimes, those could be mixed. And then, dependency-wise or operation-wise, this indeed does a lot of help for us. However, we should remember that those instances still run on the same physical hosts, and they share very valuable resources like CPUs, disk, network, and other things provided by hardware. And what's worse, they do that implicitly. And so we never know if one specific physical host is running 1, 2, or more instances of our service. And what's worse, we have no idea if there are some noisy neighbors that are running beside us. And modern container management systems like Mesos or Kubernetes do the thing even worse, and they give us no guarantee about where every specific instance is going to be located. And even if we try to build our infrastructure from scratch and we try to make it homogenized as well as possible, we are not protected from any eventual upgrades of the hardware that is going to be made in the past and then in the future, sorry, and then the hardware gets heterogenized as well. So then we try to deploy that into production. We'll let the users in, and the users start sending their requests. And as I said, round robin is one of the most popular load distribution strategies. So the load balancer starts to distribute workload evenly, and that causes that the same amount of user traffic gets to more capable instances and to less capable instances, and then users, some of them start getting responses in longer time than the others, and for some of them the error rate could be bigger than for the rest of the users. And from our perspective, some of the hardware gets overloaded, and overloaded hardware is very hard to manage. We barely can do any operations on those hardware, and some of the hosts get idle when where capable physical hardware gets less traffic than it can process. And from business perspective, idle hosts don't earn money. They have their operation price, but they don't earn that. So what we would expect is that the load balancer distributes workloads not based on where the instances are deployed, but how capable they are. Then most of the users would get more or less the same response time, and most of them will get more or less the same error rate, and most of them will be more or less the same happy. So of course we have hit that that problem because we have very heterogeneous environment due to its continuous evolution for almost 2 decades, and we were trying to figure out how to resolve this issue. And first we wanted to start with making the list of requirements to that solution, and we followed the philosophy that we should reuse as much as possible. We should not reinvent the wheels. We should not write our own load balancers because that takes time, funds, and then nobody guarantees the solution will succeed. So we want to reuse as much as possible, but we want to keep all the mission critical elements of the infrastructure safe. We don't want to screw up our load balancers or something like that. We want to be able to scale this solution with our infrastructure. We've been growing for the last 18 years, and we see how the amount of traffic grows, how the e-commerce market grows. So we grow our infrastructure with that, and we want to be able to adapt to that growth, and we want to be able to adapt to changes. We've been changing technologies, languages, and platforms we use, so we want to be able to incorporate that. The other thing we want to resolve is that most of the services have different environment, and they have different requirements. Some of them may depend on CPU, some of them may depend on disk I/O, some of them may depend on networking. And we want to be able to adapt to different service needs as well. Sorry. And the isolation that I mentioned before, it's a very useful thing because it usually allows to keep problems and bugs and other failures isolated and fenced in some local spaces. And we want to keep that isolation, we want to keep that benefit. So no problems that happen in one place should be transferred through our solution to another places in our infrastructure. And so when we started thinking about how to reuse existing parts, the first straightforward solution was to implement to reuse our load balancers, but to implement a very unique load balancing strategy. However, that's arguably a good solution because we don't want to overcomplicate that. In our opinion, mission critical elements of the infrastructure should be as simple as possible. Therefore, they are going to be as resilient to problems as they can be. And we took a look at our production infrastructure, and we noticed that there are some other parts that we have, and those parts fortunately exist in most of the modern infrastructures. And those parts are some services for discovery and configuration management, and some services for metrics. For configuration management, that could be Zookeeper, etcd, console, you name it. For metrics, let's say Graphite or Prometheus, which is pretty popular now. And every part of the infrastructure gets their configuration and information about other services using the discovery service, and every other part could store any required metrics in the metric services. And we decided that we will make our services in the way that their instances store metrics about usage of the resources they depend on to the place where the metrics are stored. And therefore, the solution looks like the following. So first of all, we decided to forget about the round robin. Round robin is good, but it doesn't work. We decided to switch to ratio-based load distribution mechanics in our load balancers. Unfortunately, all load balancers we use support that. We use basically HAProxy F5 and Varnish. That's a cache, but we still use it for load distribution. So we switched to ratio load distribution tactics, and that's basically the same round robin, but you can put some weights to your backend instances, and then the request will be distributed according to those weights. The instance that gets bigger weight gets more requests. The smaller weight, less requests. And then the quest is just to calculate those weights and set them somehow. And since, as I mentioned, instances log the usage of the critical resources for them, we could do something that gets those metrics about the resource usage, and based on that usage, it calculates the fair weight for every instance. So all the instances of a specified service get fair number of requests according to their capacity, and then when that weight is calculated, we can set that weight to the discovery and configuration service, and the load balancer gets that. There are different ways how load balancers can get weight, can get weights from the configuration services. I don't want to waste some time for that now, and could have been this simple implementation, like a really simple event loop that gets instances from a discovery service that calculates some weights based on the metrics it gets from Graphite, let's say, and then pushes that new weight to the configuration service. However, it's not that simple, because metrics that instances log, they are not real time. Frankly, there are no solution that allows you to get real-time metrics. That is always some eventual information that you get, and different services have different metrics. They depend on, some may store CPU usage, some may store disk writes, and you need to incorporate that. You also don't want to reconfigure load balancer every time you get weight, and you basically have no idea what load balancer you reconfigure. If some service uses HAProxy, you need to reconfigure HAProxy in one way. If some service uses F5 load balancers, you do reconfigure them differently. Nothing of that could be estimated. You cannot tell in advance that we will need this, and this configuration for the rest of our life and never restart this load balancers. And you cannot restart load balancers in production. If you restart load balancers, well, you're out of customers. So we decided to switch the algorithm for that, and the overall architecture of the solution looks like that. It still uses the discovery and metric services, and however, there are several separate isolated components that do the steps that I've described previously. So there is a component called instance watcher that periodically gets instances for a specified service from the discovery service, and it processes them in some way and puts to some sort of channel that then is read by another isolated service called metric watcher that gets metrics for those instances from the metric service, processes them in some way, in some standard way, and then pushes them to metric channel, which then is listened to by weight calculator that knows how to calculate the weight for that for instances of that service, and pushes the weights to the score channel. I'm using weights of score in this presentation randomly. This is basically the same for us. Then the score applier analyzes if the weight was changed significantly or not, and it knows how we should apply that weight to some specific service. And in order to simplify the architecture, we decided to call those components score and runtime. And the score and runtime basically is these 4 components, and it's responsible for calculating weights for instances of one single service. And we decided to think about implementation. How can we implement that, and whether there's a technology that allows us to use to use existing stuff without writing a lot of extra code. And you of course think it's Python. No, it's not Python. It was not Python initially. We thought that Golang allows us, this has to be Golang and Python conference, allows us to keep these components inside Go routines. It allows us to run them asynchronously, and it allows us to read some data from the channels when they are available. So when there are data, we do something. So the implementation was really simple. It was more or less this size. I removed some login and error checking here, but the code was not any bigger for every single component. We just read from the channel. This is the metric watcher. We read from the channel. If there are instances on the channel, we get metrics, we push them to metrics channel. That's it. However, we use Python in our team most of the time, and we use it for most of our projects. And regarding to that, we thought, well, it's going to be easier for us to maintain this project if it's in Python, so we don't have a lot of context switching when we work. And fortunately, Python allows to put the same components into different coroutines. And this is, of course, the feature of earlier Python, but we use Python 3, so we could easily put these components into asynchronous coroutines, and those channels could be implemented by queues that Async.io provides us. And then we use Async.io event loop in order to run all that. So implementation in Python actually looks very much simpler. We just wait until there are some data available on channel. When there are some data, we do some work. We get the same metric watcher. We get instances, we get metrics from them, and push them to metric channel. However, this was the first problem we encountered. And the issue is that, unlike Golang's coroutines, coroutines in Python are not scheduled preemptively. That means if some coroutine is doing something, no other coroutine will be able to take its context, execution context. And that means a simple call to external resources like metric service, like that, can easily block all the rest of the coroutines, and the entire system will stop working. And essentially, that could happen with some I/O code like this. So we use complicated networking schemes, and we can never trust networks. So we do something like that, we get broken in one day, and the entire Allegro goes down. So the good idea would be to put that into a separate process or a separate thread and await from there. Like the same way we await from the data from the channel, we could be awaiting here. So when there are data that comes from the metric service, we continue working. If there's no data, we release the context. However, at some point, Python community decided to not mix the asynchronous and concurrent libraries, and you cannot simply wait for the future. So future, as you probably know, is the technology, if I can call it in Python. It's a library in Python that allows you to guarantee that some result will be on some place. Unfortunately, you cannot wait from the future, and you have to use this sort of workaround Async.io provides you. And this workaround is that the event loop from Async.io allows you to run some specific part of the code that is blocking in some sort of process pool executor or thread pool executor that you can find in the concurrent module. And then some magic happens. It provides you the task you can wait, and wait is available in terms of async I/O. This, however, makes the code a little bit bigger, and if we would have to put the code like that instead of where every single line, one single line in every place we make blocking codes, we would overcomplicate the code, and it would be really hard to maintain it, and it would be very error prone. So we made a convention that most of the blocking codes are related somehow to calling external services. So if we need to call the discovery service, or if we need to get metrics from the metric service, that's a blocking call. And we wanted to encapsulate blocking calls in the clients to those external services. And the convention for this sort of solution is that every blocking call should be encapsulated inside of a coroutine that is, of course, available from the point of view of async I/O, and then the entire algorithm looks much simpler. This is the part of the score applier code. As you can see, we don't use the process pool executor here. We just await something that is provided by the discovery service client. There are important points that I would like to highlight for implementation like that. So when you write this sort of things in Python and async I/O, you should be aware of blocking calls all the time. One unfortunate line and you block the entire solution. You should never do any heuristics on error handling. Every error inside of a scoring runtime means you kill the entire scoring runtime. If one of the components stops normally, you kill the entire scoring runtime. You should never try to do any recovery. You have error, you kill the entire thing, and you let it respawn after a while. And this is basically what I said. One scoring runtime should never do scoring or weight calculation for instances of more than one service. You do that, you mix the strategies, you mix the algorithms, you overcomplicate the code, you make it more error prone, and putting more error prone code inside of the critical systems is not good. So how can we follow these points and still implement that? And we decided we would need some arbiter. And this arbiter would be responsible for two things. The first one, it's responsible for reconciliation the list of running scoring runtimes to the list of scoring runtimes that is going to be running. And what it does is reading the list of services, which is also dynamic, by the way. It gets the list of services from the discovery service, and then it compares them with its configuration. And the configuration says which exact components of the scoring runtime should be running for every service. And if some service matches this pattern and some configuration exists for it, the orchestrator checks if there is a running scoring runtime for it. If there is no, it starts it. If the configuration is different, it kills the existing scoring runtime and it starts a new one. If there is a scoring runtime that is running and there is no service that matches this pattern for that scoring runtime, the orchestrator kills the scoring runtime. This process, as I said, is called reconciliation. And again, if you do it like that, this will be more or less the implementation of the entire scoring orchestrator, minus logs, minus some error handling. All it does, does an infinite loop inside of a coroutine. It checks the list of scoring runtime. You probably don't see the code, but there's no point. You iterate over the list of services, you iterate over the list of orchestrators, of scoring runtimes, you compare them, you make them look like they should look, and then you sleep. Then, as I mentioned, the entire thing should be extensible. One of the services may need one calculation strategy, another may need another calculation strategy. And you basically can encapsulate, you can basically define these dependencies as dependencies to external services and to some internal implementation details in our scoring orchestrator. So external services means that you can require different different metric service for every service. You could require different interacting with a different discovery service for some specific services. And internal parts are calculators. You could use different calculation strategies. You could use different score appliers that analyzes the new calculated scores differently, and you want to be able to interchange that. And what we have learned from the Golang implementation is that for this sort of critical thing, you should always opinionate your interfaces for this sort of interchangeable part. Python actually allows us to not do that. You just implement something according to the specification, you throw it into the other code, and then the duck typing does the rest of the job. So it compares the types, the interfaces in the real time, and then if it matches, it works. If it doesn't match, well, you have a problem. You don't want to get problem when you run this thing in production. You want to get this problem when you start the thing or you run the tests and you see that the interfaces don't match. So Python allows us to use this very nice ABC model. ABC stands for abstract-based classes. It's in the standard library, and it allows us to define a class with some meta class, and it allows us to use very nice decorators to say, if you want to implement the class that follows this interface, you have to implement these methods. And if you don't implement them, you get the error as soon as you make an instance of your class. So it doesn't get thrown into the rest of the code. Another thing is that we wanted to be able to install different components as separate packages. Like if we have an instance of our instance scorer running, and we want to reconfigure one of the instances in some way to use a newly implemented calculator. We don't want to reinstall and redeploy the entire instance scorer. We might want to just install one library that provides the calculator and then use it. So with what I've mentioned before was that orchestration strategy, and the nice thing Python provides us, which is entry points, we can actually achieve that. And entry points is Python's way to specify, to name some pieces of the code that you have in your Python environment. And if you do it this way, you could easily say, well, this piece of the code will be named like that, and then you could refer to that piece of the code from your configuration. And say you install new calculator as a separate package. All you need to do is to use that calculator for some of the services, is to just change the configuration, and then the orchestrator will see that the configuration is different, and it will be able to use that because you don't refer to the code point explicitly. You do that, you do that using this implicit way. The calculator. That's, of course, the most important part of this instance scoring. And as I said, it could be different. And frankly, in our production environment, we use only one of them, and we call that CPU FAIR algorithm. It's pretty simple, yet very helpful. All our instances store metrics of their CPU usage to the metric service. And then we can get those metrics and put them on some scale, and different metrics may have different CPU usage based on their capacity, and then based on the information we receive from the metric service, we calculate some fair value. That means if the workload is distributed fairly, all the instances should have this sort of CPU usage. We've been using different strategies to calculate this value. Currently we use simple math based on standard deviation function, and then we put that fair value to the scale of possible weights or scores that are applicable to our load balancers, and we say that if the instance is getting the fair amount of traffic, it should get this weight that is on the middle of the scale. If, however, some of the instances have CPU usage which is different from the fair number, we should get the other weight. And if some instances are idle, they get more weight. If some instances are overloaded, that they get smaller weight. And we ran that pre-simulation, and I'm really sorry for this chart. I tried to do something with something with it, and like it's invisible probably to the people way up there. Okay, cool. So this part pictures the charts for wait, CPU utilization, and requests per second for instances that are running with no CPU fair algorithm. And as you can see, the wait is more or less the same for most of the instances, and therefore they get more or less the same number of the CPU utilization of the requests per second. However, those instances have different capacity, and so their CPU usage varies a lot. And it doesn't look like a lot here, but you should see. You can see probably that here it's 0.1, here it's 1.5. So that's a great difference in CPU usage. And as soon as we enabled the CPU fair algorithm, the picture starts getting different. As you can see, the weights got distributed. They're not equal, they're not close to equal anymore, and the 4 instances started getting different number of requests per second. However, that allowed us to get more or less the same CPU usage. So the utilization of the hardware became more optimized. Conclusion. I would like to tell a few words. So this is not a silver bullet. I always tell in the conferences that there are no silver bullets. This worked for us. This may not work for you. This may work for you. And what is good that we noticed is that this sort of load balancer approach allows you to do proactive load balancer. That means you don't wait until something gets screwed up. You change the load distribution as soon as the things start getting not in the way they should be. You separate this thing from critical parts. You don't do any changes to load balancer. You reuse load balancers. You don't do any changes to configuration systems. You have small number of extra dependencies. In our production environment, we have 0 external dependencies. We have just, I see you. We have just the code that we compiled as a Go or deployed into a container as in Python, and we ran that. We didn't have to install anything else. And this is extensible. Given that you use opinionated interfaces and you use the entry points in Python, you can install the things there, and you can you can extend. You can implement some machine learning algorithms to calculate weights. You can do whatever you want. And that doesn't work only with your custom services. We tried to install MySQL slaves, put them behind the load balancer, and enable the instance scoring using the disk usage. We didn't need that for our production, so that didn't go there. But this solution showed itself pretty good. There are some bad parts, and we managed to balance and optimize the hardware utilization for our front page. So the listings and the entire front page, the offer page looks well for different users. So you get more or less the same response time, you get more or less the same error rate. However, for some instances, for some services, it was really hard to find an algorithm to do the proactive load balancers. And as you can see, this is the screenshot from our Grafana that shows that one of the services didn't get optimized as much as we wanted. So you see that the chart narrowed, but it's not exactly in the center. So that's really hard. And I would like to, throw this in. I know if it's a good thing to show in a Python conference, but this is not like advantage or disadvantage. This is what we think about Python and Golang are good or not as good for exactly these sort of solutions. We really liked error handling in both. We were afraid that exceptions in Python will be not handled by async.io very well. It comes that if you have an exception, you handle that, you cancel tasks, and you have no problems with exceptions. If you use something like G-event, well, you're in trouble. With Python async.io, it's good. Unfortunately, for Python, for this sort of solution, you really have to watch for the blocking calls, and you really have to be careful to not screw up other coroutines. In coroutine, the scheduler is preemptive, so if you need to make a request, you make a request. You don't have to watch. You don't have to do anything extra in order to not block something. Great advantage of Python is rich data structures, which allow to do really weird things on them, and also the great number of existing libraries and integrations. As I said, you can use NumPy, you can use TensorFlow, you could use anything you want in order to integrate with that. And what we liked in Golang more than in Python for this sort of solution is interface opinionating and types. In Python, you could only implement the interface based on these methods that the classes must have. In Golang, you may specify parameters, you may specify types. And typing is an arguable thing in general. However, in our experience, for this sort of critical solutions, you really have to force people to use sometimes. There is MyPy. However, again, this allows you to add some extra steps and run that through the CI all the time and check if something is typed correct. And you can also make mistakes in typings. That also happens. I have to make this attribution for the icons. You probably can download them anywhere. And as I said, no silver bullets. Consider using this for your production environments. And thank you for your attention.
Thank you for the presentation. So just to sum up the whole presentation, you went through from round robin, from load balancers to round robin with weights.
Yes.
And in order to implement the equal load in terms of heterogeneous hardware, you implemented some scoring and adjust weights.
Basically, yes, but not equal.
Have you tried
fair.
health checks for load balancing?
Yes, but health checks is a reactive load balancer. You get health checks failing when there is a problem. We wanted to start changing the scenes when there is a condition near the problem or like halfway to the problem, not when.
Have you tried custom health checks?
We did try that. That didn't work. You cannot monitor everything. You cannot you cannot get health checks from this. Well, I said the instances log the usage of critical resources. However, sometimes you don't have access to that, and sometimes we have to log that usage of resources from some external parts. Like we have the custom executors on Mesos for our instances, and that thing logs a lot to the metric service, and we use those metrics actually because you cannot get real CPU usage from instances in most of cases. And so if you do health check to instance, then you cannot get that information. You probably cannot get some other metrics for critical resources as well. Like you basically need access to hardware. If you're in the container, you're in trouble. If you're running on bare metal, well, you may have something unless you're in a C group. Does that answer your question?
You answered it by mentioning container.
Okay.
So I had a solution with health check, but it was running on bare metal.
Yeah, well, as I mentioned, some of the services may have instances on bare metal, containers, and virtual machines at the same time. So. Legacy, you know.
Thank you. Can you just explain about the blocking code issue? Did you just hide that pull executors inside coroutines, or you rewrite your wrappers in a single manner?
We just, as I said, we encapsulate in the code. We hide all the references to process pull executor inside of our clients, and this way we can, sorry. Use the same process pull executor for all of the clients and provide the clean interface. No, we didn't rewrite anything. We didn't want to rewrite what Python gives us because again, this code has to be maintained and it has some costs. So we just this coroutines encapsulate the usage of process pull executor, and that's it.
I think that rewriting maybe in a single maybe better in future because you save your resources. I think you're about that you can use concurrency.
Yes, you can. But again, this has some costs, right? So developers have to work and maintain that. And
Okay, yeah, thank you.
You mentioned scores, and on your graphs it was like CPU usage. But what about the rest of parameters, like memory utilization? IO?
Okay. As I mentioned, for our production case, we only needed CPU usage. We've been simulating and testing other things like disk writes for the case of deploying MySQL slaves behind a hub proxy. We got the calculator that was taking disk writes into account. So if disk reads, of course, slaves don't write. If we saw that some slaves get too much, make too much of the disk I/O that they can't keep up with the request, we lowered the weight on the HA proxy. Well, that calculator lowered the weight on the HA proxy, and those MySQL slaves started to get less number of requests.
And also, when you implemented that system and launched it, how does it like affect the whole stability of your microservices? I mean, do you have numbers like we now need 20% less instances, or now we got like?
I unfortunately don't have that number. So the number what we were trying to improve is how much new servers we have to rent or buy when there's a hot season. That's basically the issue. When we start getting more and more requests, people get crazy on holidays in Poland, and they buy a lot of stuff. We're not even allowed to touch any part of the infrastructure. This is because of the workloads, and we buy a lot of servers buy or rent a lot of servers in order to incorporate that load. And unfortunately, I don't have the numbers, and I'm not sure I could have told that to you because that's some financial numbers. How the number of the services we have to rent or buy changed after that. So we see on the charts that the CPU usage for those services that are using this algorithm narrowed, and it's more or less equal for the services. What?
Amongst them. I mean, now they got like equal load.
Basically, before that, we used to have some instances overloaded, so they had like 1.5, and some of them had 0.5 or 0.8, and then it's like we try to keep it at 0.7, I think. So if it gets bigger, then it's time to scale up, of course.